singular n chains, and they can be understood as a kind of a formal linear combinations of what is called singular and simplexes with integer coefficients. And so singular and simplex is just any continuous function from n simplex to our topological space X, the single chain X, and then so this space by Cn of X, and then we introduced there was a boundary operation which from a singular n chain give a singular n-1 chain. And it had this nice property that if you apply it twice, applied it from Cn to Cn-1, and then you apply it again to Cn-2. This composition is always 0, just identically, which follows from the definition of this operation. And this allows us to define what we call singular homology for topological space of X as a kernel of this operation quotient with respect to the image. Sorry, dn plus 1. And so at the end of the last lecture, we kind of gave a general result for what is H0 of X. So we showed essentially that, let's see. So we showed that for X was connected, we show that H0 of X isomorphic to Z. And in general, we also know that we also show that in general, for we have X is decomposed into a disjoint union of path connected components, the corresponding homology groups given by the direct sum of the homology groups of individual path connected components. So in particular, for H0, if we calculate H0 of a disjoint union of path connected components X alpha, so for each of them, this will be a sum of H0s for each of them. And each of them is isomorphic to Z. So in particular, if this sum is finite, you just get Z to this power, which is the number of connected components. And OK, so let me give a few kind of comments about how kind of informally you can think about these singular n chains, what are kind of geometrically, how can you, again, informally understand them. So, so let's consider first C0. So C0, again, so this is an element, arbitrary element is of this form where sigma I here will be a singular n simplex. Have some combinations like this, where each of these guys here is sum up from a 0 simplex to X, and this is just a one-point space. So you see, The continuous map from one point space to X is just completely specified by its image. So we can understand this linear combination kind of just a bunch of points in the topological space of X weighted by some integers. And here, okay, the D0 is just acts trivially here, so we don't have to, like, every combination like this is in the kernel. 0, just that you define this to be a trivial linear homomorphism. But what about, but when we can consider homology, we consider C0 divided by image of D1, and D1 acts on one chains and gives us 0 chains. So how do we understand informally one chains? Again, so this is an arbitrary element here, again of this form. I kind of use more the same abuse notation, use the same thing here. But now here, each term here is a map from one simplex to X, and one simplex is an interval. So an arbitrary element in C1 you can consider, again, understand there's you have a bunch of intervals mapped to X, and each of them are weighted by some numbers. This. And then if I act, for example, by, let me erase this. Here, simplicities that I had. And suppose I have, of course, when I choose this, again, remember that when we talk about one simplex, we always choose its orientation. So here we choose an order, what is 0 and what is 1, what is the first vertex and what is the second vertex. And this gives us the orientation on these intervals. And then the D operation here. So for each of these guys, it takes the so again the operation of D is just given by, like, you first kind of consider the second, well, the last vertex, and you this gives you one simplex, sorry, 0 simplex with the same weight. And then you remove this vertex and you keep just this vertex, and this gives you 0 simplex with opposite weight. So this is how your D acts on this interval weighted by -3. And similarly here you will have +5 from this boundary component and -5 from this boundary component. Here similarly, +2, -2. And so in particular, this means yeah. In particular, this means that if I, for example, if I consider now the image, so what is the image of this D1? The image is generated by a pair of points which can be connected by paths and has, this pair have opposite, the points in this pair have opposite weights. In particular, if I that if I consider any some zero simplex, some element of C0, I can always suppose I consider some point with some weight, I don't say +5. This I can always change to element which gives me the same homology class. This means I change this to the same thing plus d1 of something. And so I can always change it so that I can essentially move this point along some path by preserving its weight. So I can change this point +5. Let's say everything else. And this is achieved just by adding d of this d of the one simplex whose image is this d of one of singular one simplex with weight 5, so that it corresponds to this path connecting these 2 points. So if I have a particular path connected components, this means I can these weighted points which I have, I can freely move them around. And of course, you can always by doing this this procedure, you can always bring all points to just one point, some particular m, right? And this gives you one-to-one correspondence between C0 divided by image of D1, which is by definition our H1 group with Z for just if this topological space is path connected. So this, the number here just corresponds to this kind of a total sum of weights which we have here. Okay. And similarly, in principle, you can understand the H1, for example, again, formally. So this is H1 is by definition the kernel of D1 divided by the image of D2. So how can we understand elements in the kernel of D1? So arbitrary element of C1 is again something like this, bunch of weighted paths in your X, and D1 acts like something like this. So on arbitrary element, D1 is not trivial, so it gives some sort of zero simplices from the boundaries. So the only possibility, the only way to have zero of this action is that the boundary, they coincide kind of the boundary of one of these paths coincide with the boundary of the other or the same, so that this kind of the contribution from the boundary cancels everywhere. So you can have something like well, if I locally have a kind of a picture something like this, is 3 paths which have one path. So for pair of paths, the terminal point is this, the same point this is also initial point of some third path, and they come with some weights, let's say n1, n2, and n3, and the boundary. If I act on this kind of configuration by D1, I am not going to get contribution from this for this common boundary. So this can, okay, in general, this will give me zero singular simplex, which is this point weighted by n1 minus n2, because this was in the opposite direction, plus n3. And this should vanish if you require this to be kernel. So in general, you can understand this kernel of D1, which we call as one cycles, some sort of graphs. So you can have some sort of graphs. Topological space X. Each edge is essentially weighted by some integer. This. And at each vertex, you have to ensure that the D1 acts on this trivially, you should have that the sum of these weights in each vertex is 0, sum with appropriate signs determined by the orientations of these paths, essentially corresponding to edges, which again correspond to our singular one simplices. And okay, this is, but then you also have to consider equivalence relation on such singular one cycles. And similar here, so we are allowed to add a D2 of some two chain. So we can, for example, we have something like this. We can add, suppose this has +2. One simplex. And you can consider, and imagine that here we have singular simplex. Again, this is what happens in X, and this is images of the corresponding maps. And with weight +2, and then the boundary, so the boundary of these two simplex will give me a triple of singular one simplices with the same weights, but possibly with signs, plus or minus, depending on how I choose orientation here. And so this means if I can modify my original graph by changing this kind of edge to a pair of edges like this. But I can also, in principle, I can also consider, again, we remember that here we don't have, this is a singular simplices, so we don't have any conditions that they should be one-to-one anywhere in the area. So you can actually add a particular kind of degenerated, consider in a sense a degenerated map, degenerated where two vertices, the map from triangle where all these edge just collapses to this point. And this means that in particular you can modify whenever you can kind of you can modify always deform one edge here in this graph to a different edge, provided that you can put a disk, essentially. Well, what we have here is topological disk. If you can, if there is a disk between the original edge and the deformed point. And a very easy, very simple example of an element in the kernel of D1, namely a very simple example of one cycle, is just to consider single, consider a singular one simplex, so that yes, the boundaries of the interval are mapped to the same point. And again, you can kind of you can always modify it if you can find some sort of a disk like this. So that kind of you split the boundary of this disk into two parts. And one part will be your original cycle here, and the other part of the disk will be your new cycle. So this will give an equivalent cycle. So basically, the pair of cycles, particularly the equivalent, is together they form a boundary of some disk, which map inside your topological space. Again, this is just some kind of informal nonsense, but yeah, sometimes people ask questions what is kind of geometric intuition behind these homologies. In principle, they are defined quite formally, and it might be hard to visualize what's going on. And you can continue, of course, this story to higher dimensional simplices, in a sense. Like, for example, for two-dimensional simplices, you can have some sort of, understand some sort of two-dimensional cycles which represent elements of the homology group in degree 2. You can send some sort of like forms. You can kind of have a bunch of triangles glued together. They form some sort of form. Again, you kind of modify these triangles. There is a equivalence relation saying that you can do modifications. You can change a bunch of triangles to another change of a bunch of triangles if the difference is a boundary of a tetrahedron, and so on. Okay. Any questions about this? Okay. So now we will come back to a more formal systematic study. And so, okay, we want to develop essentially some techniques to calculate homology groups. This is one of our tasks, similarly as we did for fundamental group. But we can start with something simple. Ask a question, what is the homology group of a one-point space? And the answer will be as follows. So the only non-trivial homology groups are in degree 0. And there the group is isomorphic to the group of integers. So, okay, this is one of a few cases where one can do just calculation by definition, using definition, I mean, in the case of singular homology groups, which are unlike for the simplicial homology groups, which we briefly considered, in general, they are quite hard to calculate by definition because these spaces often are infinitely generated, although the homology groups often happen to be the homology groups themselves often happen to be finitely generated. Okay, so but in this particular case, it's easier to describe explicitly the abelian groups of singular n chains. So what is Cn of a point? So we have so we want to consider the map sigma from a one-point space. Sorry, from delta n to one-point space. There is only for each n there is only one map like this. Because, well, there's only one way to map anything to a point. So this is just a Z, one single generator. There exists unique sigma for any n greater or equals than 0. Well, let's choose to distinguish this n to kind of show the dependence on n. One can fix this sigma n. So this is a group generated by sigma n as a free abelian group. Okay, and now we want. So how does dn act on this group? Well, we just again need to just act by on the generator, which is sigma n, and well, if you remember the general formula, so we have there is a sum from I from 0 to n with minus 1 to the I of 8, and then you consider a restriction of this map to the kind of is phase, which is a subsimplex where you remove is vertex. But all these guys, again, they are the same, right? All restrictions are the same because they're, again, from any n simplex, there is a unique map, and here any restriction, the restriction will be mapped from n minus 1 simplex to x. So they're all the same, and so this will be since there are n plus 1 terms with alternating signs here, the result will be 0 if n is odd, because they will just all pairwise cancel out, and the result will be sigma n minus 1. So it's a single generator which you have otherwise if n is even. So they are all kind of cancel all but 1, because there is an odd number of terms with alternating signs. Okay, good. And so this allows us to explicitly understand this singular chain complex. In general, so this is a sequence of your abelian groups. C1, 2, 3, 4, and so on. Here are the maps. Oh, sorry. Starts with C0. D0, which is again identically 0, D2, 3. Good. Okay, each of this group is isomorphic to Z. As we just showed. And the corresponding maps are like this. Okay, this is a 0 map. And then D1, so for odd n, this is also 0 map, right? Then this is even. This is a identity map because it's maps. Well, it's kind of well, identity if you identify the generator of that here with the generator of this here. Identity up to isomorphism. The zero map is the identity. Okay, so what about H0 point? Just to check that we have in agreement with what we showed about H0 in general. Okay, here, so this is a kernel of D0, which is the whole Z space, divided by the image of D1, which is a trivial subgroup. This is Z. Okay, this is an agreement because this has one path connected component. What about then? Let's consider n point. So here, for all others, as you can see, it will depend on the parity. So let's consider Hn for n odd when n is 1, 3, or 5, and so on. So this will be, let's consider, for example, here. So the again, the kernel of D3 will be the whole space, will be Z. D3 is 0, so the kernel will be the whole space C3 in particular point, in this particular case, when I assume, just take example of n equals 3. And the image, so the previous map is identity, so the image is whole Z as well. So it will be Z divided by Z. So we quotient with respect to the whole group, and the result is a trivial group. What about now Hn of a point when n is even? Let's look, for example, here when n equals 2. So the kernel here, so this map D2 is identity. So the kernel is trivial. What about the image of the previous map? Well, the image is also trivial because this is 0. This is a trivial group divided by the trivial subgroup, and this is 0. And this is indeed what we wanted to show. So all groups are trivial except the H0. Any questions? So as I mentioned before, so in the study of homology, it will be more, we'll have more algebra. And so we will produce, I'm not sure if we already had this notion in some other course, but let me nevertheless introduce this definition of exact sequence. So a sequence of homomorphisms as follows. So we have a bunch of, have a sequence of groups So for our applications later, we can always assume that these groups are abelian, but in principle, not required for this definition. And so the sequence of groups labeled by integers. We have maps between them, which are homomorphisms. Between groups AI called exact if and only if, by definition, the kernel of, for each n, the kernel of alpha n is equal to the image alpha. The kernel of any map here, which is a subgroup here, coincides with the image of the previous map, which is another subgroup. We make the following remark. So we already kind of considered these sequences of abelian groups with a homomorphism between them, which we called chain complexes. So for chain complex, this was not required. What was required, there was required the inclusion. These alphas, which were maps, which were called boundary homomorphism, and there was required inclusion here. But in principle, this can be, in principle, be a particular case of of a chain complex. So if chain complex exact sequence then homology groups trivial. Well, this is obvious by definition because, well, here for a chain complex, we define as a quotient of the kernel over the image. But if they coincide, all these quotients are trivial. And there is often, one often encounters a particular class of these sequence of these exact sequences, which are called short exact sequences. An exact sequence form zero A B 0, where 0 means trivial group. So here we will work mostly with trivial groups, so it's kind of customary to denote the trivial group by 0, not by 1. Is called short sequence where there are only 3 non-trivial groups. Well, let me give you some simple example of short exact sequences. Particularly, we have the first place is Z, and the second place is also Z, and the third place is Z2, so it's a cyclic group with 2 elements, and the first map will be a multiplication by 2. And the second map will be taking a number mod 2, right? So both of them are, they all are indeed homomorphism. And you see that so if I take element here, some number here, it will go to to A, but if I take any number here, let's say B, it will go to B mod 2. And the composition of these maps is trivial. And moreover, the kernel of this map is exactly the image of this map. So the kernel of this map are even numbers, and this is exactly the image. Another example. All groups will be finite. Something like this. And take also here multiplication. So this is, I understand, usually in our course we use this notation as the n determines the group of numbers modulo n. So here, again, the first map I can take multiplication by 2, and the second map is I take mod 2. And but we notice that one can in principle consider so these the first and the third group can be the same, but the group in the middle can be in principle different. I can take in the middle also just the product of these groups. And here as a generator, well, let's say the generator here 1 I can take it to 1, 0. And so that 1, 0, which is one of the generators here, will go to 0, but 0, 1, another generator will go to 1. And it's easy to see that this is also a short exact sequence. So the kernel of this map is exactly the image of this map. Any questions about exact sequences? Okay, now, as we did for fundamental group, we want to kind of understand the relation between homology groups of different topological spaces. And this, in particular, will allow us to do calculations later on. Suppose there is a map from topological space X to Y. And then one can denote what is called induced map. So far, this is not a map on homology groups, and this is a map on the corresponding chain complex. It's a map from chain complex of X, a singular chain complex of X in degree n to the singular chain complex of topological space Y, also in the same degree n. And well, the idea is similar to what you do for fundamental group. So here, arbitrary element here is a linear combination, formal linear combination of maps from delta n to X. And what you can do, you can compose each of this map with your F, get a corresponding singular chain Y. This guy was a map from delta n to X, is this composition will be automatically a map from delta in Y. But we, of course, our goal is to define some sort of induced map on homology groups. To do that, we need to kind of study how this kind of composition, how the related to this boundary. So that essentially this composition is respects this boundary homomorphism, which we use to define homology groups. This is essentially given by this following proposition. So let us write first spin complex for X. This. One, again, one, so on. And just below it, we'll write the same for Y. Here again, we're using the same notation, but of course this is different maps because they are between different spaces. So in principle, if you want to be pedantic, you can write some additional index, which indicates for which logical space it is defined, but we will usually suppress this. And okay, now we already defined the induced maps between groups, the abelian groups of singular chains fixed degree. Again, we all denote them by this F sharp, but of course, again, this is actually different homomorphisms. And we want to show that this diagram is commutative. Big diagram with a lot of horizontal maps and vertical maps, but it's commutative, so particularly it doesn't matter how we go. We go like this or we go like this. The composition is the same. So how do we show this? Well, again, as usual, just take any generator here and act on it by this composition, and then by this composition and show that the result is the same. Take not to take a generator, just a one singular simplex delta n X. And let's see. Well, okay, so we need, let's fix notation for its vertices from V0, V1, and Vn. And then, okay, so let's go first this direction. So we will first apply dn. Actually here, right? Sigma is a generator here. First, go like this. Apply dn and then F sharp on our sigma. Okay, we first apply d, and by definition, we'll have sum from 0 to n minus 1 to the I. Then we take sigma. Okay, this is separate this. It's not confusing. Like sigma, and we restrict it to a space where we remove vertex. Okay, good. And then we apply F sharp to it. Again, we just use linearity. So by definition, F sharp is linear. So I just can apply it to each term. And this sum over I, take my sign outside, coefficients also outside. And here, what I need to do, I need to compose, by definition of sharp, I need to compose this F, restriction of sigma subsimplex where removed is vertex. But of course, I can first, it doesn't matter, I can first do this restriction and then compose. So I can first compose and do a restriction. It's the same. Because I do a restriction on a domain of, just do a restriction on the domain of my map, which is n simplex. Means first restrict and then do composition. And this is first composition and then restriction. But this is, here you can recognize a definition of my Dn. Homomorphism acting on the position of F sigma. So if you this is already dy here. And here I had the and this same as a composition of, I first apply F sharp and then Dn. And this is indeed shows the commutativity of the diagonal. Basic idea is just the F sharp induced map is by definition is linear, and the D operation is defined just involves some linear taking linear combinations and taking restrictions on our subsimplices. And of course, the composition commutes with restriction. Any questions? Now we are ready to define the induced map between homology groups. Again, a map from X to Y, then define we also call push forward map push forward of F. So the name again is the same as for variable group, and the notation will also be the same, just star at the bottom. You can also call it induced map, induced map, or induced homomorphism. The map from Hn of x and y, and it's defined as follows. So I take a class represented by some singular chain beta in X. I map this class to F sharp beta. Here is an element of the kernel, by definition, the element of the kernel of D is a subgroup in C. Principle for what we know, just definition of F sharp tells us that this is some element Y. Okay. So this is how we want to define it, but of course we need to do some checks that this is actually makes sense. So one first, as usual, we need to check, okay, this is well-defined, so in the sense that it doesn't depend on the choice of the representative. But we also want to check that this is, for this to be represent actually some element in Hn of y, this should be not just an arbitrary element of Cn of y. It should be element in the kernel subgroup, the kernel of D map. So we need to check this stuff. Only has the following remark. This is well defined. First, again, let's check that this is actually in the kernel of the boundary homomorphism. Check. Zero. Okay, but we already showed that these two guys commute. Change the order. Again, you have to be careful, they commute, but of course this is Dn acting on chains in Y, and this was Dn acting on chains of X. Again, as usual, you can just suppress, but and this is, well, by construction, this beta was, since beta represents an element in homology, D of it must be 0. Good. And now we need to check that it's independent of the choice of representative. Take instead, take beta plus dn of, I don't know, some gamma, sorry, dn plus 1 of gamma, so this will be an arbitrary element image plus 1 instead of beta. Okay, and we will have to see where this guy will go to under spiral. Okay, so just by definition, I have to take this guy and apply F sharp. And then, okay, of course, I can use again the linearity. And then I can use, again, the fact that we show that this F sharp can be exchanged with D, or boundary homomorphism. So this is one of gamma. And now this is an element in the kernel, sorry, in the image of Dn plus 1 acting, again, to be precise, this is acts on the chains Y. And by definition, this is has the same class. Factor out such elements. Class of just F sharp or beta. So this is means that indeed the map is well defined. Any questions? Now we, as we define this push forward, we can show various properties, and very similar to what we had for the push forward of the fundamental group. So suppose the first property is that suppose we have a triple of topological spaces x, y, and z, and a map G from X to Y and F from Y to Z, and then the statement that the push forward of the composition is the same as composition forwards. Second property is the identity map from X itself is push forward identity homomorphism homology group of X, let's say for some fixed degree n. Again, if you wish, tells you that the like the language of categories here, this just tells you that this the homology is a functor from the category of topological spaces to the category of abelian groups. The proof is quite simple. Well, the first property is, yeah, I mean, the proof is almost tautological. Okay, let's see. So again, we need to check it on just arbitrary generator. And for a generator, take some singular and simplex in X. Well, we first consider, how the induced map acts on chains first. And for this, let's consider just an arbitrary generator of the group of singular chains. So in this, of course, by just the usual statement about composition of maps, the composition of F and G and then composed with sigma is the same as the composition, taking first composition of G and sigma and then compose it with F. And from this, this immediately follows that induced map of this composition of F and G, induced meaning it's induced on the singular n chains. So it's the n of x. That is the same as composition of the corresponding induced maps. So it's just equality between homomorphism between like this between this pair of abelian groups. And but then it follows, since we remember, if you remember that the push forward, it was just defined by taking the class of the F sharp applied to the corresponding representative. Then immediately from the definition of the push forward, it follows that the same is true for push forwards on the homologies. So yeah, as I said, it's kind of the proof is kind of tautological. And the second property, you first do the same. Okay, if you apply the, you can compose, if you compose identity map from topological space X to itself with a sigma like this is the same as sigma. And therefore, you can means that the induced map, the induced map with respect to the identity on X is identity on the group, and the identity homomorphism on the group of a singular n chain of X. And then again, since the push forward on the homology groups are just defined by taking this induced map on the chains and composing it and applying it to the singular chain representing an element in the homology, this automatically gives us the forward of the identity is identity homology. And this concludes proposition. Any questions? Now, again, as it happened for fundamental group, the homology will be actually not a kind of it will be homotopy invariant. In particular, it will have the similar property respect to homotopy between a pair of continuous functions f and g from x to y. So suppose f and g are homotopic. This implies that the corresponding push forwards are just the same. So it's a equality between homomorphisms hn of x to hn of y. Okay, so this will require some work to prove this. So, okay, so they're homotopic. Then by definition, there exists homotopy map from x times an interval to y. If we restrict f to the beginning of the interval, you recover f. And if you restrict f to the end of the interval, you recover g. And okay, this is, and we'll essentially want to use it to show this equality. And for this, yeah, we'll need to do some preliminary construction. So, so we consider so the homology group has something to do from these maps from these n simplices, and the homotopy has to do something with the map from an interval. So let's combine these two things together and consider this product. And so let's so you can understand this. Let me show an example. N equals 2. So this delta 2 is just a triangle. And consider this triangle times interval. Like this. And okay, we want to distinguish the simplex at the bottom and the top. And we will do this by choosing a different notation for the corresponding vertices. So at the bottom, we will choose vertices labeled by V0, V1, and so on. So this is example. This will be V0, 1, 2. And for the simplex at the top, you will choose notation with W, W0, W1, N, so that these vertices with the same index, they form a boundary of an interval, of a copy of this 0, 1 interval. W0 is exactly on top of V0, W2, and W1 is on top of 1. So if you want to consider P a projection, formally what I said means that if we consider projection from this product to delta n, canonical projection, this means that the projection of I is the same as projection of WI. Now we want to subdivide this space into simplices. So this can be prism. The subdivision can be described as follows. So this product, the union of n plus 1 simplices with the following with vertices of the following form. So we first consider a sequence just of vertices the same as we have here in the bottom simplex, and we go v0, v1 till vi. But then after this, after vi, we take wi, and then we will continue with the same order as we had for the top simplex. So we can vi plus 1 dot dot, sorry, wi plus 1 dot dot wn. So you can see that here the total number of vertices is n plus 2. So this is indeed n plus 1 dimensional simplex. So how does this look in this example? So let's see. So here, so I here goes general I can take it starting from 0, n. There will be n plus 1 simplices in total of this form. So here, this will be subdivision. In this example, there will be a subdivision into 3 simplices. And OK, let's take what is first, I can see the I equals 0. So the vertices I have to take it would be B0, and then I immediately follow with W0, and then I continue with W's. H as a final W2, and this is it has this vertex, this vertex, this vertex, and this vertex. It forms together. They form the following tetrahedron, which I draw in red. Now I take I equals 1, so I have 0, V1, and then I take W1, W2. I have to take this vertex, this vertex, this, and this, form tetrahedron. This. Then I take I equals 2. 0, V1, V2, and then at the end I insert W2. Has these 4 vertices, which form this yellow and you can see that we covered everything, the whole prism, the whole triangle times an interval. And then we will use this subdivision to define what is called prism operator. It will be homomorphism from the group of singular n simplices in X, group of singular n plus 1 simplices Y. As usual, we'll define it just a generator, and then it's extended by linearity to an arbitrary chain. Okay, and so this generator here is again a map from delta n X, and the result is given by the following kind of heavy formula. So there will be sum I from 0 to n minus 1 to the I. So it's kind of, in a certain rough sense, it's similar to the formula which we have for the boundary homomorphism. It's a bit more complicated. And here you consider the composition of F. Reminder, F was our homotopy. Like this. Is sigma cross identity map interval, which is and this product of maps. I think here I consider this restricted to one of the n plus 1 simplices in my subdivision prism. So let's see. Okay, this is a bit heavy, but let's see why this makes sense. What is written? Okay, sigma is a map from delta n to X. So sigma times identity on the interval. This gives you a map from X times an interval. Sorry, delta, the simplex times an interval to X times an interval. Right? You just, sigma is just a map which you use sigma to map points in delta n to X, and you just act by identity on this interval. Just follow through. But from this space, this product, we have a F, our homotopy, which takes us to Y. And then we can compose this stuff, of course, to go directly from delta times interval, which is our prism, here to Y. So this is a map. So this is some map. Well, it doesn't matter. Yeah, gives me some map from a prism to Y, and then we can restrict this map to sub-simplices in this prism. It doesn't matter where I put my parentheses, because as we already know, the restriction and composition, they commute with each other. Maybe more nicer to put it like this. So the whole thing, it gives me this, each term here indeed can be understood as a map from delta n plus 1 to Y. Delta n plus 1 is one of the n plus 1 simplices in our subdivision of this prism. Does it indeed make sense? And well, after this, we'll need to do essentially some algebra. We'll probably, not gonna finish. Yeah, I don't want to rush this. So we'll probably finish it next time. But let me just announce what we will need to show. We'll need to show is the following identity between homomorphisms. We want to show this identity as an identity between homomorphism from Cn of x to Cn y. This kind of tells us that okay, we want to show that we'll need to show our goal is to show that f and g gives the same induced maps on homology. But f and g they don't give the same induced maps on the groups of singular chains. But what happens is their difference is can be given by the essentially commutator of our prism operator in the boundary homomorphism. And so once we show this, so this will be next lecture, and this will be essentially just some algebra. Once we define this map, we'll just again apply this all the terms to some generator, and we'll show that it's indeed the same. But yeah, once show this, it will immediately essentially follow that the corresponding induced maps on the homology groups are the same. Apply it to a class A in beta, so this is by definition G sharp of beta. And this is so we will need to check this. And F sharp, class of F sharp of beta. But then we can use this. The fact that the difference is given by stuff, so this is the same as G sharp of beta. This follows from this equality that we will prove. Same as G sharp of beta plus P equals D of beta, PD of beta plus dP. But this is, so B is in the kernel of D, so this is 0. And this is in the image of D. So this gives me the same, is equivalent to 0 in homology. And that's how we'll get the desired result. But again, yeah, more details will be in the next lecture. Are there any questions at this point? Well, if not, that's it for today.